Oh, Ace. I don't think they have. So, I was going to share. So, Jackson, we're thinking about making chairs, and if we made chairs, we just need enough so that half the class could have them, really, and then the other half we could share. Ada, when you wouldn't get a chair.
Oh, but
We were talking about making chairs.
check up there. They might have some wood just kind of like on standby.
Possible. Let's see. Sometimes these are called stargazer chairs. Sometimes they're called Viking
I think they're
chairs.
missing some context here.
Yeah, probably so. So people it was requested last week during the blue classes that maybe we could have class outside, and which is okay with me if we have weather that people are happy with and we have chairs to sit on. So this is about the simplest kind of chair you could make. So that's just what it looks like. You have one piece of wood and another piece of wood, and you cut a slot in it, and it goes in. The drawback to this chair is it's depending on the proportions, it's pretty laid back. But you can sit up straight in it and not lean back, and then you can lean back. I think it's called the Stargazer chair sometimes because of the reclined nature of it. But look at this. We should make Viking chairs like that.
Yeah.
There's a simple one. Let me look up Stargazer chair. I think. Oh no. Well, here are a few examples. But here it's also called a Viking chair, which I guess is the most common name for it. But it's really easy to make, and maybe we could improve upon it. This one looks like it's a little more upright than the other one. All right, back to. Oh, I just need to go back this way to get to my website. Maybe back some more. Back some more. And
Don't you have your website open?
which? Oh, it's there. Never mind. All right. So the bird. Why doesn't a bird get shocked on a power line? You could technically, I mean, don't do it, but you could do what the bird's doing. You could just grab onto a power line and hang from the power line, and you'd be okay as long as
You're not touching the ground.
you're not touching the ground. So, and that's the key with the bird. So why does it matter? Well, if the bird touches the ground, what happens then?
The electrons flow through the bird.
Yes. So I should, let's see, just for those people who want to try to draw on the board. This new camera setup isn't great, but it's okay. Just feel like I should draw. Oh my. And that's all right. I'll just let that. This will be a psychedelic drawing I'm going to do here. So, if this is the line, we haven't gotten into currents and circuits yet, but you could just imagine that here's oh, that's the other claw. This is one bird claw. This is the other bird claw. Here's a bird leg. Tail feathers coming down here. Wing. Another wing. This is where I'm going to lose it. Should I do a lower beak too? There we go. It's not a bad bird. Oh, it's got a weird chin though for a bird.
It's a pretty good bird. Yeah.
There we go. All right. So anyway, there's the bird, and there's going to be current flowing through this. We haven't gotten into currents and circuits. Just imagine that there's some really strong source of, actually, I could draw this, really strong source of negative charge over here. So there's negative down here. So electrons are flowing through this wire, and they're flowing to sort of a positive terminal, or you could just imagine, really, that somewhere here they're flowing down into the ground. So source of electrons is kind of like a really high concentration of them, and then they're traveling to the ground, which is neutral, but in this case is less negative than this wire. So when the bird is there, why don't some of these electrons go into the bird? Do you think the bird is as negative as the wire? Anybody have an answer to that one? Yeah, what do you think, Jack?
Is it because it's neutral?
Because so if the bird is neutral,
Oh, there's
shouldn't
one.
some electrons go into it just like they go into the ground?
It's more negative than the ground, and so the electrons want to go to that higher source of positivity.
Right. And yeah, and this is a trick question. So the bird and the ground are kind of this. As soon as the bird lands on this, if we imagine the bird is neutral, electrons do flow into the bird. So you have some electrons going into the bird. And pretty soon, after the electrons flow into the bird, what happens to the bird's charge? It becomes negative. And then what happens to the electron flow?
They leave, right? Or they just stay.
They stop flowing into the bird. So they're going to get to the point where it's so negative that they're not going to flow into it anymore. Is the same thing going to happen with the ground? Is the ground going to become negative? No, because it's this vast reservoir of positive and negative charges. So the negatives that go into it just spread out really quickly through the ground, and it doesn't change its charge at all. So it can keep sucking more and more and more out. The bird really quickly is just a little bit of charge is going to go into the bird, and it's going to get charged up basically, and then it's going to stop. So it's not even going to feel like it's being shocked because that's so insignificant, the amount of charge that's going to flow into it. If the bird, on the other hand, reached down here with the really long claw and touched the ground, then the electrons would have a good path to get to here. I mean, really, this end of the wire and the other end of the wire are a long way apart. So this is probably, it's got miles to go before it ever gets to wherever this current, you could think of it as going. So it'd be a much closer route than if the electrons could just flow like that through the bird leg. And that would just keep on frying the bird, because this is going to keep accepting more and more, and this is a source of lots and lots. So that's how you die if you're the bird. Somehow touch the line and the ground, or anything else for that matter. So
Another bird that came onto that bird would happen.
if another bird landed on this bird, another bird on top of this bird's head, as long as it's not touching the ground, it would be okay. But if a little bird down here reached up and grabbed that bird, then they'd both die. Unless it was touching with something, a really good insulating claw, that the charge couldn't pass through very well. Okay, so let's see, was there more to that? Oh, and if a bird landed on a Van de Graaff generator, would it get shocked?
No.
What if I leaped through the air and touched the Van de Graaff generator? I should try this later. Like if I ran past and I jumped and I went boop while I'm in the air, would it shock me?
No.
I wouldn't think so, because I wouldn't be connected to the ground. It would be like, well, wait a second. I think it might. So the Van de Graaff generator, yeah, no, I think we could do this, and I think we could actually test this later on. But it's a little bit different. These high voltage lines, how many volts do you think are out there?
A lot.
How many volts in power lines? I'm just going to do near houses, because they're different depending on whether they're the really tall ones. So typical voltage for long distance are in the range of 155,000 to 765,000 volts. The one in a neighborhood are less than that. I think they're like 10,000 volts. So voltage of local transmission lines is 13,800 volts. How do you think that compares to the voltage of a Van de Graaff generator? Higher or lower?
A whole lot higher.
Voltage of Van de, there we go. Glad I didn't have to type that one more time. 50 to 150,000 volts. So, as people are fond of saying, it's not the voltage that kills you, it's the current that kills you. So when I touch that, if I let it charge up and I go over there and I get shocked, there's 150,000 volts potentially going into me, but not a whole lot of current. And we're going to get to this in the next unit where we do circuits and things. So the current is the total amount of charge that flows through you per second. And the voltage is more like the pressure with which that's pushed along. If you think of water flowing, you can have a really high pressure squirt of water. Let's see. So I'm getting this in. You could have a really high pressure quick squirt of water that sprays out on something, or you could have a low pressure garden hose spraying out on something. And even though the power lines that are coming over, they have less voltage than the Van de Graaff generator. If you touch those, you're going to have lots and lots of flow through you. If you touch the Van de Graaff generator, it's just a small amount of charge pushing into you really quickly, but not just reaming you out basically and killing you. So back to that, I would say we'll try it later on, but I'm not going to try it while my camera's hooked up. Ada, I'm sorry you're not getting to see some of the demonstrations with the Van de Graaff generator, because it just kills all my electronics here. So in a little while, I'll start it up and I'll leap through the air and touch it. Or maybe Jackal
I'll do it.
or somebody else wants to do that. I don't know.
Thank you.
Avery, you want to try that?
I'm good.
All right. Well, anyway.
I'll let Jack do it.
Yeah, I like to get shocked.
So
We can probably also.
I'm guessing it's going to have enough of a voltage difference that it is going to shock us. Sorry, I've lost my way. That's Friday. Friday we get to come back to this cute cat. Yeah.
When's our test?
The test is going to be Thursday. We're going to have a test on Thursday. So this is this week in reverse. Friday, we're doing some stuff with string instruments and waves. Thursday, a test. Wednesday, nothing unless people want to show up to do a review session. We'll do that over a meet, but there's no new stuff on Wednesday. Tomorrow, we're just going over, I'll hand out some notes for the instruments so that blue people will have them on Friday. And then go over the practice test, which you're going to get to work on today, and do a little bit of review for the test. And here's today. So today, one of the main things is to go over the homework, which was 18.7 and 18.8, the practice. I'm going to get my solutions out, and if anybody wants me to talk about how to solve these or show you in a different way than the solutions show you, I'd be happy to do that. I had a lot of good questions asked during advisory today about these problems, so I think there's, especially in terms of what an electric field is and what the direction of the electric field means and how you answer questions like number 2 on 18.8, how you figure out that the field is toward the surface of the earth, that kind of thing. That seems to be giving people problems, and that's not unusual. That's normally a tricky concept. So the homework was to do 18.7 and 18.8 practice, and I'd be happy going over any or all of these if you want. Which ones? Some of you in here have already asked me your questions. So, Mo, number 2? Okay. On 18.7, this number 2? Oh yeah, okay. So this one, I should probably get an extra sheet of paper too so I can draw another picture. Maybe I can fit it on the bottom. This is a kinematics-y kind of problem. And on the test, I'm going to narrow down the number of kinematics formulas you might have to use and really restrict some of the information that comes from other units that's going to be on this test, because I have 3 students who, for different reasons, were not in my class last quarter. And I don't want this test to depend too much on stuff from other quarters. So I'll give you a clarification about that tomorrow. But this is an example of stuff coming from other quarters. Here's the kinematics formula. There's another one in here that, there's Newton's second law right there. Another one in here that is, where is it? There's an orbit problem. No, it's this first one. No, it's centripetal force. And anyway, I'll be pretty specific on what kinds of things from other units, what equations you might need to use on the actual test. So in this one, we've got an electron with initial velocity. So we've got V0. Looks like kinematics are going to come into play. And it's really fast because it's a small thing that can accelerate very quickly. It doesn't have much inertia. And a uniform field of this many newtons per coulomb. So this is E. And the field accelerates an electron in the direction opposite to its initial velocity. So its initial velocity is positive rightward. At least that's the way I'm going to envision it, because this is a positive number. What's the direction of the electric field? All right, so right off, this is probably the trickiest part for a lot of people. As I've been explaining it all day, just using my fingers, if you think of my fingers as electric field lines, and assuming that they're arrows pointing to our right, what this means, just by convention, somebody decided, let's make the lines point in the direction in which a force would be exerted on a positive charge. So if the field lines go to the right, if this is my electric field, that means any positive charge placed in this field is going to be, it's going to feel a rightward force. So what causes this field? We don't really know for certain. There could be a negative charge over here pulling that positive to the right. There could be some positive charge over here repelling that positive charge and pushing it away. Or there could be both. There could be a positive plate and a negative plate, and this positive repels the positive and this negative attracts the positive. But back to the most important point, the direction of the arrows showed the direction that a positive charge would be pushed. So the direction of a force felt by a positive charge, which means if you have a negative charge, it's going to feel the opposite, which intuitively quickly makes sense, but also if you think about what's causing this electric field, if there's an electric field to the right, making positive things go to the right, then, and that's a negative charge over here pulling the positive charges, it's going to repel a negative charge. And if this field is created by a positive charge that's pushing away positive charges, that's going to attract a negative charge. So hammer this into your head. The direction of the electric field is the direction that positive charges get forced, and it's the opposite of the direction that negative charges get forced. So back to this is saying that our electron is moving to the right. This is its initial velocity, and the field accelerates the electron in the direction opposite its initial velocity. So this is the acceleration, this is V0. So the acceleration is in the direction of the force. The force on this electron, and by the way, F sub E stands for, in my notation, it stands for the electrostatic force. So this is the direction of the force an electron feels. An electron's negative, and negative charges feel a force that's opposite the field. So the field is going to the right. So this is kind of confusing, and Mr. Pennington doesn't really even say right. I don't think he is, when he tells us this velocity, he must not be too serious about it being positive and therefore to the right. He's just saying that the direction of the electric field is in the direction of the initial velocity. And sort of a simple way to get at that is if the field accelerates the electron opposite its initial velocity, then any direction that an electron, which is negative, gets accelerated is opposite the field. So if it's accelerated opposite its initial velocity, then the field is opposite its initial velocity. It seems like this is straightforward to me, but when I talk about it, it feels like I sort of am clarifying it and then muddying it up again. So Mo, how about that first part? Does that make sense? Or did I just screw it all up?
Yeah, I understand that.
Okay.
No, I got it. Thank you.
Okay. So, do you want me to go on with B and C too? Mo?
No, that's okay.
So that was the biggest part, A?
Yeah, I just got confused. I think the little drawing at the top kind of confused me, but when you explained it, I got it.
Right. Yeah, the drawing at the top it's pretty minimal, and without anybody there to explain the context, it's kind of hard. It's like when you join a physics class and people are looking at Viking chairs and you have no idea why. Okay. Any other problems that I should touch on? Well, I feel like I want to share some things that came to light when I was talking to somebody else about this. I feel like I should go over a few of the parts that are like this. So unless I get asked about these, I'm going to search through for things asking about direction and really go over some of the direction parts. Adawin, what's your question?
Sorry, I noticed that. I put a question in the chat.
Oh, I'm
Can you
sorry.
go over from 18.88?
Yes, I'm sorry. I haven't been looking at the chat. I'm not really good at that. So number 2. Yeah. So this is one I wanted to go over anyway. Let me grab another sheet of paper as well. If I think about forces in this unit, there are a couple of formulas for force that come to mind. From the new unit, there's the formula for the electric field, which is force over charge. So this just says the electric field, which is going to be in newtons per coulomb, is force divided by charge. And you can rearrange this if you want to isolate force. You can say multiply both sides by little q, and you get the electrostatic force experienced by something is equal to the electric field multiplied by the charge. And this is going to work out, this is the number of newtons per coulomb, and then you multiply it by how many coulombs you have, and then you get the number of newtons in the end. It's like miles per gallon multiplied by the number of gallons. You can figure out how many miles you can drive. It's that kind of thing. Because all this is a ratio of how much force you have for every unit of charge. The actual force differs for different charges. So here's one force formula, and then the other force formula for the electrostatic force is Coulomb's law, kq1 q2 over r squared. And right off the top of my head, those are really the only two formulas for force in this unit. And these problems have, they've hearkened back to the Newton's laws problems that we did before. And they're going to involve some force, and basically we're going to have to set something equal either to this or to this, depending on what we have. So in this particular situation, we're being asked about electric field. What's the direction and magnitude of electric field that supports the weight of a free electron near the Earth's surface discuss what the small value for this field implies regarding the relative strength of the gravitational electrostatic forces. So in this case, we're supporting the weight of an electron. And I don't think I need, well, maybe I will. I'm going to redraw Mr. Pennington's picture. It's going to look very similar. Here's the electron again, and there's the ground. And if we didn't have some intervention, this electron would just fall to the ground. And the thing that would make it fall to the ground is its weight. But since its weight is being supported, it's in static equilibrium. So we've got one force, the downward force acting on this is its weight, which is just mg, and that alone would make it accelerate to the ground. But it's being supported by the electric field, which is creating another force. So there's this electrostatic force coming from the electric field, and this is it's strong enough so that this is just exactly as strong as that, so that the net force on the electron is 0. It doesn't move up or move down. So let's see. So what are we looking at here? So since we're looking for electric field, and I mentioned there are a couple of different formulas for force. There's the electrostatic force equals the electric field times a charge that's creating the electric field. And then there's K Q1 Q2 over R squared. The one that makes sense to use in this situation is this one, because this one doesn't involve the electric field at all. So the force exerted on a charge, in this case this electron, so this force is equal to the electric field that's around here. I'm not drawing it yet because I haven't really decided which way it's going. It's equal to that electric field times the charge. So I'm just going to write Q, but Q is the charge of an electron. So I just set this equal to that, and then I solve. So that's really the easy part. EQ equals mg, and I think Mr. Pennington wrote that out, but he wrote it QE equals mg. And then he's just algebraically solved for the electric field first by dividing both of these sides by Q. So he gets E equals mg over Q. And then he can solve for E. But so this is one instance in this problem where we're taking something from this unit, one of these forces, and we're setting it equal to something from a previous unit. The orbit problem, we're not using mg. Let's see. Yeah, we're not using mg. We're using mv squared over r. I just wanted to point out that that's sort of a common theme here in these problems. All right.
So will this be on the test? Like,
I'll be really specific about which kinds of things you'll be responsible for.
okay,
I'll go ahead and tell you now there won't be anything orbiting, and nothing where you have to use a centripetal force formula. I won't include that. And I'll be really clear on which formulas you might need to know how to use. So the harder part of this problem, figuring out the direction of the electric field, let me just talk through that. So we have this electron, and it needs to be supported by the force exerted by an electric field. And going back to what the electric field means, I'll draw it pointing to the left again. I'm just going to draw an example electric field. If you see this, if you see arrows going to the left, that tells you the direction that a force would be exerted on a positive charge. So the direction of an electric field is always opposite the direction in which a force would be exerted on a negative charge. So if I put an electron in this electric field, it would be pushed to the right, opposite the field. So thinking about that in reverse, what we need a force that pushes the electron up. We need this field to create an upward force on the electron, which means we need a field that would pull a positive charge downward. So what we need is a downward field. So if you just remember that electrons or negative charges always experience a force opposite to the field. If we need an upward force here, that means the field has to be downward. Adewin? Do you have any continuing questions? Is there anything I can clarify? Okay.
Sounds good, thank you.
Okay. And even though I'm not going to put it on the test, and I'll just go ahead and say that very clearly. This is the other, it's a similar kind of thing. In this particular case, we have a positive, this is the nucleus of a hydrogen atom, which I think is an interesting problem. I'm glad it was in here, because this is something you can do with this stuff that's kind of cool. So you have an electron orbiting the atom, and if you remember from the circular motion unit, when you have something in a constant, a circle with constant speed, uniform circle, then the net force equals mv squared over r. And that's also the centripetal force. So in a case like this is the net force. And the specific kind of force that provides that force is the electrostatic force. So when we did this before, we had the sun and then we had a planet going around it, and we would set mv squared over r equal to the force of gravity here, which we could write Newton's law of universal gravitation. But in this case, the electric force is K Q1 Q2 over r squared, where we've got the charge of this, the charge of that. Those are the two charges. R is the radius between them. K is Coulomb's law constant. So that force equals the centripetal force. So that's what he's doing here. He's just setting centripetal force equal to this other force and then solving. So remember, there are two ways that I can think of right away to do electrostatic force. One is this, and then the other one is that, using electric field. We weren't given any information about electric fields here, but we were given a lot of information about the charges. One's an electron, one's a proton, and you're given the mass of an electron. So in this case, the electric field equation wasn't helpful. Seems like there was one other one with direction that I wanted to talk about. Maybe it's this one. Yeah. So number 3 here, the Earth has a net charge that produces an electric field of this, 150 newtons per coulomb, downward at its surface. Oh man. I'm going to try to push it and see if I can get how much life. 10%. That 10% goes fast. But I'm going to see if I can get done. So the Earth is like this, the field is like this, and it says, what's the magnitude and sign of the excess charge, noting the electric field of a conducting sphere is equivalent to a point charge at its center. So we're just imagining that at the center of the Earth there's some charge. Is it positive? Is it negative? So these downward field lines, those are the direction that what kind of charge gets pushed. Positive or negative? Somebody say it. Positive. So if positive charges are getting pushed down and the Earth is causing this, then what charge does the Earth have? Negative. So that's how you figure out the sign of the excess charge on the Earth. It must have a negative excess charge if it's going to be pulling positives down and creating a downward field. So does anybody have other questions? I'm going to plug in my computer. I think that the direction of fields, that's the hardest thing. So while I'm plugging in my computer, the assignment starting right now is to do Mr. Pennington's practice test. And I won't take up any more of your time because it's going to take a while. So you've got class time and then you've got homework time. I was going to turn to it. It's the last thing in the packet. It's several pages, but it's got a lot of space too. So in Google Classroom, there should be a link to the solutions and also the, make this bigger. Also a couple of videos of me going over the sections. So this first link is the answers to it if you want to check them. Then I've got another link to the multiple. Oh no, these are the same link, multiple choice. I'll have to fix that.